Welcome to the third shift, which is insightful masterclass by Your Story and AWS. Today we are joined by Alex Casalboni, and he will be talking about reusable serverless patterns for web applications and data analytics use cases. All this while considering cost optimization and security best practices to look for during implementation. Alex is a senior developer advocate here at AWS and is an amazing tech passionate colleague of mine. Since 2011, he has been building web products and helping other builders learn from his experience. He often speaks at technical conferences across the world, supports developer communities, and helps them build applications in the cloud. His love for coding spreads across Python and JavaScript communities. He also actively contributes to a lot of open source projects like AWS Lambda Power Tuning. He co-organizes serverless meetups in Milan as well as the Serverless Days Milan. He's particularly interested in serverless architectures, machine learning, and data analytics. Thank you for joining us today, Alex. We are excited to hear you. Over to you.
So welcome to this webinar. I am Alex from Italy, and I'm going to talk about serverless architectures and some reusable patterns for your web apps and for your data analytics kind of workload. I think these two topics are quite related to each other. Usually you need some sort of data analysis or data ingestion kind of subsystem in your websites, and so we'll talk about those one after another, but they might be part of the same architecture actually. Where do I come from? I'm a web developer, software engineering and data science background. I've been in the startup world for about 4.5 years in a Silicon Valley based startup. It was fun, and I've been a customer of AWS for a lot of years, and now I joined about a couple of years ago. Cool. So you can find me mostly and everywhere on social media, Alex Casalboni, mostly Twitter and LinkedIn, but I appear elsewhere sometimes. So first of all, I want to make sure everyone is on the same page when it comes to serverless computing. What do we mean? What are the fundamentals so that we can talk about how we build a website and how we build a data analytics pipeline with these concepts in mind. Okay. I can see your questions. So if you have questions, you can use the chat interface. Feel free to ask me anything. I'll try to keep an eye on it. Okay. Cool. So what is serverless? Maybe you heard of it. If you are here today, maybe you have an idea what it is. Maybe you are already using it for some prototypes, or maybe you are in production already. I would say if you've never heard of it, the super easiest way to think of it is it's just a new abstraction layer that allows you to focus on building your application without having to take care of the whole infrastructural stack, from the hypervisor to the physical machine hypervisor, operating system, container orchestration. Okay, all of that does not exist. With serverless, you focus on the application layer because everything else is managed by the cloud vendor, which is AWS in this case. So as a developer, what we want to do is to focus on the business logic. Okay, that's what adds value to your product, to your application, to your service, to your whatever you're doing. I think it applies very well to enterprises as well as startups, as well as consultancy companies. Whatever you're doing, you might actually benefit from serverless architectures. And it's not all true or false. It's not like you are either 100% serverless or 0% serverless. There is kind of a spectrum there. And if you look at the compute spectrum on the cloud, on AWS, you will find on the left what we call everything that runs on EC2. And well, if it runs on EC2, it's not really serverless. Okay, it's kind of the other side of the spectrum, because you have to spin up instances, install your software or your framework or your application on it, and then you have to maintain it, patch the virtual machine, and apply security updates and all those kind of things. And then there is a middle area where you find a lot of managed services. And here, some of these services can be considered serverless, or maybe they operate also in a serverless way. For example, Amazon DynamoDB. You can use DynamoDB in a managed way with provision capacity, but you can also use it in a fully serverless way with on-demand capacity. So sometimes the difference might be actually a bit tricky to spot. But in this area, you find services that do a lot of work for you. They automate operations, they automate data backups, they maybe automate the patching of the underlying infrastructure or compute instances. So this is still a very good area to be, in my opinion, especially if you want to gain speed of development. And then you have the fully serverless world. Of course, it's not only AWS Lambda. So what happened is that there were already a lot of serverless kind of services before 2015 when AWS Lambda was announced. But think about Amazon S3. You didn't really have to spin up servers or maintain the underlying infrastructure with S3 since 2006, 2007. But if you wanted to use S3, you still had to spin up a virtual machine, or you still had to spin up a fleet of containers and so on. So what really triggered this idea of a fully serverless architecture was AWS Lambda in 2015, because now you also had the compute component that was operating in a serverless fashion. So that's what we call function as a service. That's the compute component of serverless, if you want to think it that way. But then you have a lot of other services that provide additional capabilities like authentication and authorization, streaming, data ingestion, or distributed tracing, or storage, or RESTful interfaces. So this whole platform of serverless services allow you to build application in a fast way, and also in a way that scales when it comes to cost in a linear way with your business. So most of, like 99% of these services, they don't cost you anything if nothing is happening in the system. So most of these operate in an event-driven fashion, like Lambda. So you actually pay for Lambda only if there is an event that is triggering your Lambda functions. And for all the other services, usually you pay either, I don't know, per number of users or per gigabytes processed, something like that. So that really, if you are a low scale, it's really, really cheap. It might actually be free if you are in the free tier. And then as long as you scale, it will scale linearly or even sub-linearly, because usually discounts apply with higher volumes. So, usually there are no surprises. It's still very important to be able to estimate cost, and it kind of pushes you into being aware of how many API calls, how many requests per second, or how many, I don't know, gigabytes of data you're going to process. The good news is that estimation is not needed for capacity planning reasons. It's mostly needed for cost estimation purposes, which is already a huge difference with respect to the previous architecture, previous way of building applications, because you actually needed to estimate all those things just to know how much physical hardware you had to buy, or how many virtual machines you had to launch in the cloud even before you went live. In other words, serverless allows you to not care about servers or containers or orchestration. You don't have to provision, you don't have to manage or patch the underlying operating system and infrastructure. Because of that, because we take care of that part, it means that the service itself, the compute service, but also the other services, are horizontally scaling in an automatic way. So you don't really have to worry about that scale. Of course, there are cases at hyper huge scale where you want to be aware of how quickly or how much you are actually scaling, because of course there is no magical world of horizontal scaling where any scale is supported. There are boundaries that you need to be aware of, but to get started, it's basically like you don't have to care about the scaling. We also like to say that you pay for value because you don't pay for the idling compute capacity. as I mentioned before, you only pay when something is happening, which means, if nothing happens for a month, you don't pay your bill for a month, which is pretty cool. And that also allows businesses like consultancy companies to provide POCs for free, or it allows startups to operate for months or even years, keeping the cost super, super low. At the same time, and this is the fourth thing in my slide that a lot of developers forget, you get for free, by default, by design, a lot of high availability and high, security best practices that are inherent in the system. So you don't have to worry about multi-availability zones, architectures. You don't have to spin up a lot of virtual machines to make sure you are resilient to regional or local failures in individual availability zones. So Lambda and all the other serverless services take care of that for you. Okay, but who's been adopting it? So I don't really have time to go through the list, but I can tell you that the largest majority, actually 9 out of the 10 largest AWS accounts are using serverless. So maybe if we talked 3, 4, 5 years ago, when serverless was really just a little new way of doing things, very unstable and very new and very uncertain in a way. 5 years later, it's been adopted by major companies, major organizations, and a lot of these companies are happy about it. A lot of these companies are pushing to adopt it even more in different projects internally, or different, even their own all the other companies that work with them, because you get a lot of agility and you get a lot, you don't have to think about all the old problems of IT basically. But enough non-technical stuff. Well, one last thing, you actually get a full ecosystem of partners and system integrators and monitoring solutions. So it's not just what AWS can provide, it's also about what the rest of the ecosystem has been building in the last 5 years. So you have a deployment and development frameworks like the serverless framework, or monitoring solutions like Stackery or Hexagon, or there is a lot going on. So keep an eye on this space if you're new to it, because there is really a lot. So let's get into the technical side of things though. So what happens in practice when you want to run a Lambda function? So you provide the code, which could be in basically any programming language. It could be in Python, Java, Go, Ruby, .NET, PHP, whatever language you want. If a language is not supported, you can even provide your own custom runtime. I've heard of a couple of customers running their COBOL code on AWS Lambda, so they can basically migrate all their mainframe application to Lambda. I don't know how easy that is, but if you're using most of the popular programming language, it's 99% supported. You can always bring in a custom runtimes, and the community has done a very good job at creating new custom runtimes. So what happens is, hey, you want to run your function, your code, but before we can do that, we have to kind of download your code somewhere. It's on S3 usually. You upload it to S3, and then we can start a container, which is actually a micro virtual machine powered by an open source project called Firecracker. And then we can bootstrap the actual runtime, depending on which programming language you have chosen, if it's a Python, Java, Go, and so on. Finally, we can start your own code. And this first red phase here does not have to happen every single time. It happens every now and then. It happens if you're scaling horizontally very quickly, so that we need to spin up new Lambda runtimes. But once your function is warm, and this has been executed at least once, we can just go straight to executing your code, and that will make your Lambda execution, your function execution faster. So the best thing of this, in my opinion, is that the whole process happens in a bunch of milliseconds. Okay, it's not like a virtual machines that would take a few minutes. It's not like a container that would take maybe, I don't know, 20 or 30 seconds. Okay, this whole process from downloading, started bootstrapping, and invoking your function takes 2, 3, 400 milliseconds. Okay, that's the magic of it. That's the technology that's powering this kind of a revolution, if you want, in the last few years. Also be aware that because it's a simpler model that abstracts away a lot of the complexity, you don't really have access to the underlying infrastructure. So you cannot really choose how many cores, what CPU you need, if you need a GPU, if you need more or less memory, if you need more or less network. All you have is, I like to call it, a power handler. We actually call it memory for some reason, but in fact, in practice, it's a power handler. So it goes from 128 megabytes of memory to 3 gigabytes of memory. Okay, but remember, by giving your functions more memory, you're actually giving them also more compute capacity, more networking throughput, more I/O, and so on. And this is especially important because you pay for Lambda based on 100 millisecond intervals, right? So if you run for 170 milliseconds, you're going to pay for 200 milliseconds. And this is super important because if you are able to run twice as fast by giving your function more power, it's very likely, because the cost is proportional to the power that you give your functions. It's actually very likely that you're going to pay the same. Sometimes it's actually even cheaper, or sometimes it's, I don't know, 50% faster and 30% more expensive. And you can find a balance between these two dimensions. I was actually pretty frustrated with this idea of how do I find the optimal power configuration for my functions. So I built an open source project that was already mentioned in the introduction. It's called AWS Lambda Power Tuning, and it really allows you to be data driven in this decision. So it takes your function, executes it in with different power memory configurations, and then it comes back to you with a result suggesting the optimal configuration. It also comes back with a interesting visualization of the results, with the execution time, execution cost on average, and you can find the optimal trade-off. Visually, it's way, way easier. Cool, let's get into the web patterns, which is the topic of today. So what are the patterns for web applications, which also means RESTful APIs or microservices? These concepts are very, related to each other. Let's look at the standard, starting point for a web application on AWS with serverless. So usually you want to separate backend from front end. So the typical architecture looks like this. You have your customers, your clients, usually in a browser, or it could be also a mobile application, but let's stick to web application for now. So usually you have your front end, and because it's a modern application, you can serve that front end as a static website. Static meaning that the assets required to run on the browser are not dynamically generated on the fly. Okay, you can compile or your client-side application once, then you can put it on S3 or on some object storage, and then you can distribute it using a CDN, for example, Amazon CloudFront. You can build these applications however you want. It could be using a React or Angular or Vue.js, or even your own HTML files built manually. Whatever works for you. The most important thing is that we are decoupling the front end from everything else that is dynamic, APIs, databases, all the back-end stuff, because this will make the responsiveness and the speed of this front end much, much better. Okay, we want to decouple it, not only because it might be developed by two different teams that might have different skill sets and different structures, The only interface that you need between these two systems is usually the RESTful API. So as long as you document very, very well the RESTful interface, the APIs, the parameters, the payloads, the response, you can be pretty sure that these two projects can proceed in parallel, possibly owned by different teams. And usually the backend is structured as follows. You have a RESTful layer, you have the application, the business logic, and that is usually implemented with Lambda. And you probably want to have some dynamic data, some data storage. A database could be relational with RDS, data engines like MySQL or PostgreSQL or MariaDB and so on, or it could be NoSQL like DynamoDB or MongoDB or Cassandra or all sort of other options. So this is the typical, if you think about it, this is the typical three-tier architecture, but implemented with cloud services. So you have the client, you have the backend with this could be Nginx, this could be your I don't know, Python server, and this could be your database. Now it's much easier though, because these are managed services that are going to scale horizontally for you, each and every one independently. I haven't mentioned, but usually you also want to have some sort of authentication authorization, and Amazon Cognito, I believe, is one of the best options. There are also third-party options like Auth0 and many others. Cognito is well integrated with the platform. It does a couple of things. First of all, it manages all the users' data for you. So password, custom fields, sign up, sign in, log out, password forgotten, all these things that you would usually re-implement over and over for every new project, multi-factor authentication, all these things managed by a single service. But also it allows you to provide your client-side code with temporary credentials to be able to invoke your backend services. So this is a static website that would go and authenticate with Cognito, get some credentials in the client side, and then it's able to invoke your APIs. Of course, some APIs could be public, but usually most of your APIs are going to require some sort of authentication. There is another interesting option here if you spot the difference. So in this first option, we had CloudFront only serving the static website. There is actually an interesting way of putting CloudFront in front of both backend and front end. So one super simple reason you may want to do that is because you avoid a lot of CORS, cross-origin kind of issues, because both your backend and your APIs and your services are going to be on the same origin, on the same domain. So this simplifies a little bit, but maybe it's not enough to justify it. You also get the benefits of using CloudFront. Maybe you may want to cache some of your read or your get API endpoints, responses, or maybe you want to integrate other CloudFront features like Lambda attach, for example. So Lambda attach allows you to customize the behavior of your CDN distribution with a very, very similar approach that Lambda provides. So you can only use, if I remember correctly, JavaScript and Python. You cannot use any other runtime at the moment, but it allows you to customize how the request is handled before it hits or misses the cache, and how the response is going to be transformed and cached by the CDN after it's returned from your backend. So you can do a lot of interesting things. You can customize headers, you can do A/B testing, you can do a lot of interesting, funny things with Lambda attach. So if you put CloudFront in between both backend and front end, a lot of options open up. Let's focus for a second on API Gateway here, because it's a very sophisticated and interesting service by itself. It's not just a RESTful APIs, it comes with a lot of other features as well. So for example, there are 3 different types of endpoint that you can choose from. So the default historical one is the edge optimized. Edge, because if you use edge optimized, you want to optimize the latency for a global audience, for browsers and customers and clients that are everywhere around the world. So under the hood, an edge optimized endpoint is going to use the Amazon global network, the AWS network that also CloudFront uses, for the CDN. On the other hand, if you already know that your APIs are going to be accessed only from a specific region, a geographical region, or even from a specific AWS region, because maybe it's a service to service kind of integration. It's not a customer, but it's another internal service that you develop. It doesn't really make a lot of sense to have a CDN to go out into the internet and then come back to a data center of AWS. You can actually use a regional endpoint. Okay, there is no CDN. It's very, very good and very much even faster for in-region kind of services that need to talk to each other. Third option is the private endpoints. Okay, in this case, we do not want to expose these APIs to the general public anywhere on the internet, but you only want to expose these APIs to specific VPCs or specific services that are inside your AWS account. So this is what the edge optimized architecture look like. You have a hidden CloudFront distribution in between managed by AWS. And then, of course, it always go back to the AWS region where you have deployed the application. Another interesting way to use the regional endpoint is also if you want to build a multi-region architecture, maybe with a active-active or active-passive kind of setup. So for example, what I could do is that I would deploy the same application to 2 different regions. So I don't know, imagine Oregon and Virginia, or Dublin and Frankfurt, or I don't know, Singapore and Sydney, okay? And I deploy exactly the same application, and I can synchronize the data using some sort of multi-region data replication mechanism, for example, using DynamoDB global tables, but now there is also the same for Aurora, there is also the same for Elasticache and Redis. And what you can do then is to route requests to these 2 regions using DNS. Okay, I can configure Route 53 to send requests to the right region based on different logics. Okay, I could say use a latency, lowest latency routing. So if I'm closer to this region, I'll be routed here. Or, and this is great for an active kind of setup where all your regions are actually serving traffic in an active way all the time. Another way could be, hey, always serve traffic to this region, but if something goes wrong, if a deployment breaks, or if the database is down, if the application layer is broken in this region only, please route the requests to the backup region, to the passive region that is just waiting for something to happen before traffic comes. So this active passive setup is great to increase availability, to increase the resiliency of your applications. And I think it's great that you can do it with serverless architectures, because if you think about it, this passive region is not generating any traffic until there is a problem. And because it's serverless, it's not costing you anything to keep it up and running, because there is no HTTP request, so you pay nothing for API gateway. There is nothing triggering your Lambda function, so you pay for nothing there as well. The only thing you're paying here would be the data replication, right? So you want the data to be already synchronized there when you start driving traffic to that region. So in that case, you're probably paying for some write request to your DynamoDB global table, but that's part of the equation. You get additional resiliency, you get additional high availability, and that's the cost of it. The third private endpoint is pretty interesting if you want, for example, to integrate an API gateway endpoint with your on-premises data center, for example. So you connect your VPC to AWS Direct Connect, and then your private endpoint to this VPC. and you can call API gateway from your on-premises data center. Pretty cool. Okay, let's talk about security as well for a second. Let's go back to our standard web application without any strange trick. So usually you want to serve your website with HTTPS, with secure encryption. So CloudFront provides that out of the box, and you can also integrate CloudFront with ACM, Amazon Certificate Manager, which is one of the very few free services out there in the platform that will manage your certificates, will renew your certificates when they expire. So I think it's a pretty handy service. But not only that, CloudFront comes with a lot of interesting features when it comes to protecting, for example, some content that you don't want to be served to anybody. So, for example, you can sign URLs that only a specific user that has that sign URL can access. So I don't know, maybe imagine that on S3 you have also put some video content or some video courses. Let's make a simple example. But you want only paying customers to be able to access that video content. Well, great. You can use sign URLs so that you generate a sign URL for one customer that maybe will expire after a few days or after a week or after a month. And then you know that only that customer with that URL will be able to access that object on S3. And you can even bound those sign URLs to specific IP addresses, and there are other options too. But you also get a lot of other features like DDoS protection, because it's a global CDN distributed worldwide with more than 200 edge locations around the world. We can make sure that your backend and your services and all your resources are protected from external attackers. So that's also another interesting feature. S3, I don't think I have to go into the details of how granular your S3 permissions might be. In this case, it's a public website, so it's quite likely that you want to provide, world public access to your S3 objects. But you can always put a private folder in your S3 bucket and make sure that that private folder is only accessible maybe via sign URLs, for example. API Gateway, I mentioned already a lot of sophisticated features. I think especially when it comes to rate limiting and throttling and configuring custom limiting for specific groups of users, of clients. So for example, you can classify your clients in plans. We call them usage plans. And then you can say, okay, customers in this usage plan will have this throttling, or this rate limiting, 10 requests per minute. And then another group of users, my premium users, they will have, 100 requests per minute. Okay, so you can configure different throttling and rate limiting mechanisms on a group basis. And all of that is super simple. It's done via API keys. So you have not only the authentication mechanisms provided by Cognita, but you can also provide different clients and different customers of yours with individual or group API keys so that they are immediately recognized as part of a group or of a usage plan. Lambda, you have a lot of permission boundaries here too. So by default, a Lambda function cannot invoke any other service. It's able to do HTTP requests to other external APIs on the internet if it's not in a VPC without an internet gateway. But by default, for example, it cannot invoke DynamoDB. It cannot read or write data into a database. So what you can do is you have to provide specific access to the resources that each and every Lambda function needs. So if this function only needs read access to this DynamoDB table, okay, you can provide only that. If another function needs, I don't know, write access to S3, okay, great. You provide only that permission to only that function. Okay, so you can be very, very granular here, and that's actually what we recommend. Least privilege configuration for every single function. Of course, if you need environment variables, or if you need to centralize the value of some configuration parameters, there are services that allow you to do that. For example, the System Manager Parameter Store or the AWS Secrets Manager. You can basically just delegate and centralize those parameters there, and then fetch the value of those configuration parameters at runtime. There is even now a pretty cool service called Amazon RDS Proxy that integrates pretty well with AWS Lambda. So if instead of using Dynamo, if you're using a relational database on RDS, you can very easily configure Lambda to talk to the RDS proxy instead of talking to the database directly. So for example, the RDS proxy will take care of fetching the database username and password for that specific RDS database, and you don't have to hard code anything in your Lambda function. So I think that's pretty cool. Well, most databases on AWS also have some data encryption and granular permissions. I think Dynamo might be the one database with the most granular permissions of all. So not only it's encrypted in transit, the data that you send and receive from Dynamo, but it also encrypted at rest, and you can configure super granular permissions on who can read or write. So you can say this function can read from this table, but only some specific fields. So very, very granular. We mentioned the authorization and authentication capabilities of API Gateway, but if those are not enough, if you need more, there will also the possibility to have custom authorizers or Lambda authorizers. So basically what would happen is that before, your client will invoke API Gateway, but before invoking your backend, API Gateway will invoke another Lambda function that is an authorizer function, okay? So before that happens, usually your client is going to talk to an identity provider. Usually the identity provider provides a token that proves your identity. So your client is going to include that identity token in the header of the request, and your Lambda authorizer is able to read and fetch and verify that token. So that token might be a JWT token, a JSON web token. In that case, all you need to do is to verify the validity of that token with a private key. So no additional requests here, but in other cases, you might need to invoke and verify the token directly with the identity provider. Or you might do other things. You might have a table in between to store groups or additional functionalities related to a specific identity as well. After the authorizer comes back with a policy of what this specific identity can do, API Gateway will talk to IAM and eventually pass the request on to AWS Lambda to serve the request. So I think this is a pretty open and a pretty flexible way to manage custom authorization logic, and you can implement basically anything with it. Okay, but what if my requirements are slightly different and this serverless model doesn't work? There are a lot of cases actually where, maybe serverless is not your first option, okay? And I want to be completely honest with you, there are some. So let me go through some of these. So let's imagine that you just need a CMS. You want an out-of-the-box CMS like WordPress or Drupal or Magento or whatnot. Okay, so maybe you don't want to build another whole CMS with Lambda or with all these serverless services. In many startups, for example, I see that they want to decouple entirely the backend or the product itself from the front end side of things, like the homepage and the contact us, the mission, who are we, kind of pages. And those pages, maybe you don't want your CEO or your head of marketing to depend on the product team or the developers to change and update and do a little edit to your homepage. So for example, you might need a CMS, and there is a service, AWS Lightsail, that just allows you to spin up a CMS in literally 3 minutes. So have a look at Lightsail if you need a CMS. Maybe don't build a whole new CMS from scratch. There are a lot of cases where what you have is a monolith, like a monolithic application where everything is bundled together: the user management, the homepage, the product page itself, the database, and everything is a big monolithic application. And it might be worth it to migrate and refactor that application to run on Lambda. There are actually ways like Zappa, if you are using Python with Flask or Django, that allows you to take your Flask or Django app and kind of lift and shift the whole application to Lambda. There are other options like Serverless Express, or other options for other languages like Java and Spring. But sometimes that's not ideal, or sometimes that's not even possible because of some dependencies, because you have long running processes that need to run for more than 15 minutes, which is the current maximum limit, maximum execution time of Lambda. So there might be reasons why you want to stick to a full stack monolithic application service like Elastic Beanstalk. Okay, don't be afraid of that. It's still there, happy to use it. Sometimes though, what you want to do is you want to build a team that is building on serverless service from day one. So the option that I just gave you is that to use API Gateway and Lambda. But API Gateway also integrates with any other AWS service. So you might have a direct integration between API Gateway and S3, or you might have a direct integration of API Gateway with Fargate or ECS or EKS or any other compute service out there, or even direct integrations with other AWS services. For example, Kinesis. Okay, you don't have to go through a Lambda function to put your Kinesis records to Kinesis data firehose or Kinesis data streams, and we'll talk about these services in a second. But just remember that API Gateway allows you to build these direct service integrations as well. On the other hand, a lot of teams that I know, that I meet every day, are keen on building a team focused on front-end development, right? I hear some noises, guys. So if you're connected. I think someone is connected. Okay. Let me text them. Okay, maybe we fixed it. Okay, so I keep meeting a lot of teams that prefer to focus on the front-end side of things. So maybe you hire 2, 3, 4 front-end developers, and they really want to focus on building a great experience on the client side, on a great mobile application or a great web application. So if that's what your ideal team looks like, you can use a service like AWS Amplify, which is actually multiple things. It's a CLI tool to automate the deployment and the provisioning of cloud resources without having a very deep backend background. It's also a front-end library that you can easily integrate in your front-end code, either mobile or web, like React, Angular, Vue.js, and so on. But it's also a static website deployment platform where you can take your web application, for example, and host it on Amplify console. And maybe you will be happy to just have, instead of a RESTful interface where you need to define all the RESTful endpoints, get, put, post, blah, 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 you can, for example, adopt GraphQL, which is a new kind of paradigm where you define your schema, which is shared between backend and frontend, and then your mobile and web applications will fetch only the data that they need by providing queries or by providing mutations to that data model. That's pretty powerful if you think about it. And there are tools like Amplify that allows a front-end focused team to be completely independent and completely proficient with provisioning cloud resources. You can just say, hey, Amplify, add some storage, Amplify, add some authentication, or add some CDN, delivery network. So you can do a lot of things without being fully aware of technologies like infrastructure as code and cloud formation and all that backend world. I've mentioned Amplify Console. I think it's great. And the best part of it is you don't really have to use AWS Amplify, the other two building blocks to use Amplify Console. So if you have a static website implemented with any technology and hosted anywhere, it could be hosted on GitHub, on Bitbucket, on GitLab, almost anywhere, basically. You can even just upload a zip file with your code. So they made it very simple to connect your Amplify console application to your Git repository, even to individual branches. So you can even configure Amplify console to automatically deploy specific branches or even all the branches in your Git repository to a subdomain of your website. Things like dev.mywebsite.com or myfeature.mywebsite.com. So every single feature branch, as soon as you git push, might have a preview branch in a subdomain. So I think this is pretty awesome as a feature by itself, but you also have automatic builds, continuous integration, integrated with Git. You have email notifications, you have environment variables, you have password protected domains. So maybe the feature branch or the testing or staging or development environments, you don't want those to be public, and you can protect them with a simple password as well. So I think it's a pretty cool product. Have a look. Okay, let's talk a little bit about data ingestion and data analysis as well. Usually with websites, you also want to collect data, either to understand what's going on, or maybe because there are specific events like a sign up or a click on a button or a scrolling event or anything that might happen in the client, and you want to track it in the backend to collect some data, to visualize the flow of what the user is doing, or even just to update what the user is doing, to be able to give it some points or to be able to send an email automatically. So there are a lot of use cases there. So usually the first step is data ingestion. How do I ingest all these events, all these records or data points that I want to ingest, store, maybe analyze in real time? So in Amazon Web Services, you have a family of services called Amazon Kinesis. And each and every one has its own pros and cons and its own use case. Today, we're not going to focus on the video side. That's kind of another world. We'll focus on streaming data. We'll focus on archiving data without writing even a single line of code with Data Firehose. And we'll also talk about analyzing data in real time with data analytics. So real quick, what do these services do? Yeah, let's start with Firehose. This is one of my favorite services out there. You basically have your record producers, usually a website or a mobile application or a server or a Lambda function, whoever, and they can put records into your Kinesis Firehose delivery stream. And you can configure Firehose to deliver data, incoming data, to a destination, which could be Amazon S3, could be Redshift, our data warehouse, it could be Elasticsearch, it could be even another S3 bucket that would take that will keep a backup of all this data. But the best part is you can connect a Lambda function to this Firehose delivery stream to transform or enrich the data before it is actually delivered to the destination. Of course, this lookup table is completely optional. Okay, it's just an example. You might just use this Lambda function to skip some records or filter some records, or maybe manipulate or enrich some records, okay? Or change the format maybe. So pretty cool. It is completely serverless. There is no capacity planning. There is no shards, number of servers, number of shards to configure. You only pay for the amount of data being processed. So as I was mentioning at the beginning, if there is no data going through Kinesis Pharos, your bill is going to be zero. Pretty cool. A few best practices. Well, you can tune after how long Pharos is going to flash the data into the destination. So you can tune the buffer size and you can tune the buffer interval. I think the minimum might be 30 seconds and the buffer size should be like 5 or 10 megabytes if I remember well. And by tuning these, you may make Pharos, more or less real time, more or less heavy on your S3 bucket. Of course, if you wait longer, you will do fewer Lambda invocations or S3 put requests. So that might affect also the other resources around it. But usually the defaults are pretty okay. And I think it's great because with one click, one checkbox, basically, you can enable compression and encryption. And you can also enable a transformation of the data without any Lambda function involved, just to convert the data to a Parquet columnar format. And this is great because if what you want to do with this data on S3 later is to analyze the data, the Parquet format will allow you to do that in a faster and cheaper way. So super cool. The other service is Kinesis data stream. Okay, so in this case, what you want to do is not to directly archive this data to S3 or Redshift or Elasticsearch, but you want to process this data as it comes. So you configure a Kinesis data stream and you can connect a Lambda function to it. Remember, this is not a queue. Okay, it's not like a queue where you put messages and Lambda will take a message at a time to process the message. It's not SQS. SQS is completely different. Kinesis data streams also comes with a retention period, okay, up to 7 days. So if I connect another Lambda function, they are not going to pull messages faster, okay? They are going to read exactly the same messages because every consumer in this model will see all the messages, all the data in the stream, okay? So don't think of it as a queue or as a buffer. It's slightly different. It is not, though, completely serverless because you have to configure the number of shards. And the number of shards also means how much data you can put and how much data you can read per second, basically. You can also configure the batch size of how many records are going to be consumed by your Lambda function. So from 1 up to 10,000, okay? Keep in mind that if the consumer fails, the next invocation is going to fetch exactly the same records, okay? So if you take 100 records and you process 80 of them and then you fail, you will refetch the same 100 records, okay? So keep in mind, ideally the execution of these processors should be idempotent, or you should keep track somewhere else of which records, which items have already been processed. Keep that in mind. In case you want to process as much data as possible, as quickly as possible, as I mentioned, you cannot simply add another function because that additional function is going to read exactly the same data. It's not going to be able to pull data in a faster way. So what you can do is adopt the fan out pattern. So basically you put a Lambda function in here in the first layer that will act as a dispatcher. So it will read data without actually processing it. And then this Lambda function will invoke another layer of Lambda functions that will take care of the actual processing, okay? This is actually available as an open source project on GitHub, so you don't have to reinvent it. Okay, it's available. You can just fork it and customize it. Let's dive into the real-time kind of thing, side of things. So with Kinesis Data Analytics, the third service of the family, you can basically analyze real-time data with a simple SQL query. Okay, I think this is pretty powerful. So what you can do is you connect the producer to it, then you configure a SQL and SQL query, and the result of that query will go to a Lambda function. Let's make an example. Let's say that you have buildings around the world, and every building has a few rooms, and every room has an IoT sensor that is detecting, pressure and temperature and stuff like that. Okay, imagine that all these sensors are going to put records into the stream. And then we want to send out, I don't know, maybe an alarm if the average temperature in a building is above or below a given threshold. How do you do that? So you can do all of that by a simple SQL aggregation query here. And then your Lambda function will receive the aggregated number per building, so the average temperature per building. And your logic here will just be if average temperature bigger, larger than, I don't know, 25 Celsius, send a push notification to an operator, maybe. So let's have a look at the query that you can actually build. So it's basically regular SQL with some little modifications, but the core logic of it is pretty straightforward. So you can select whatever you want. You can set up an interval. In this case, it's a 10-minute interval. In our case, maybe we want to have a shorter interval. If it's a temperature warning, maybe we can do every 10 seconds, okay? And then we can do aggregations like sum or count or average or whatever we need to do. And then we can group by, we can apply where clauses and order clauses and so on. So I think this is pretty powerful, and it allows you to really reason on real-time incoming data with a simple language that everybody knows, like SQL, without having to do complex distributed logic with microservices or Lambda functions. So the Lambda function will receive the simple output of this query every 10 seconds or 10 minutes or whatever you need. Now let's have a look at how we actually analyze data at scale, maybe historical data. I wanted to introduce you to the concept of data lakes because that's very aligned with the idea of serverless. So what's a data lake? It's pretty close to the concept of data warehouses. If you are familiar with data warehouses, it's like a big database, but it's not a database. That's the fun part of it. The goal is always to collect, store, consume, and analyze data. We can actually store not only structured data, but also semi-structured and unstructured data. And we can do all I'm going to share because the compute part of the system and the storage part of the system have been decoupled. So they are managed differently by different services with different pricings and constraints and advantages, of course. We want to make the ingestion as fast as possible. And the most counterintuitive part is that you define the schema of your data, not when you need to write it to ingest it, but later when you need to read it to consume it. Okay, this is very counterintuitive if you come from a database or data warehouse world where you need to define the schema before anything else. Okay, no, here we can write the data and then think about a schema later. Well, not think about it, but at least define it later. I always recommend thinking a little bit about the schema before you start ingesting data, but because you can define and refine it later, you can start ingesting as soon as possible. And it's kind of a complementary to the concept of data warehouses. Well, if you want to make a data lake serverless, everything revolves around S3. S3 is where we are going to store all our data. It could be hundreds of objects, it could be thousands or even millions of individual objects on S3, and every object might contain one record, 10 records, 100 or 1,000 records, it doesn't matter. Okay, what we want to be able to is to ingest data quickly, store it securely and durably on S3, and then be able to query that data with another service that is serverless as well. So there are a lot of complementary service to this idea of a serverless data lake. I've already showed you how we can do data ingestion quickly and cheaply and without writing any line of code, just by using Kinesis data firehose that will put data into S3, compress it, encrypt it, transform it to columnar Parquet format for us so it's ready to be analyzed. Now I want to show you how to actually analyze it by using a service called Amazon Athena. So there are actually multiple options here as usual. Athena is one of the options. You could also use Redshift or Redshift Spectrum, but I think Athena is the simplest way to get started with this. So we start from data stored on S3. Now we need to define the schema of that data, what the columns are, what the types of those columns are. And you can automate that by using another service called Glue, AWS Glue. So Glue has a feature called Glue crawlers. So these crawlers are going to fetch all your data on S3 and define the schema for you, and even version the schema for you when the schema changes. And then because we have defined the schema, kind of like a virtual table, we can use Amazon Athena to query that virtual table. But remember, there is no data ingestion into another system. The data is always going to be on S3. And the good news is that once we run this kind of queries with SQL using Amazon Athena and the data is on S3, we can use the output of those queries to visualize our data with tools like Amazon QuickSight. That's a data visualization, data exploration tool. Now, Athena looks very simple. The interface is very straightforward. You have tables and schemas on the left. You have a big text area to insert your query and a big button to run the query. And then you get the results down here. So very straightforward. It's like a virtual database. It's actually based on a project called PrestoDB. And it's like an SQL interface on top of your S3 objects. So let me show you a query with Athena. So for example, in this case, I'm using an open data set that is already available on S3, and AWS is paying for the storage of this data set. I'm using the Google Ngrams data set, but there are many more data sets if you have a look at registry.opendata.aws. So here I'm doing a select. I have an aggregation sum from this table. I have a where condition, so I am selecting a subset of the data set, and then I'm grouping and I'm ordering. Okay, simple SQL. Now this query will run in about 45 seconds. Okay, if you try to run this on your laptop, I haven't tried, but it's probably going to take a few hours. Okay, that's kind of the scale, because we are operating over 170 gigabytes of data. And that's only considering the where clause, because we are only filtering one ngram. We are only scanning 170 gigabytes. If I remember correctly, the full size of the data sets is in the order of 3 or 4 terabytes. Because of this, we are paying for this query about 85 cents of a US dollar, okay? And we pay that much, which is not actually that much considering the query we are doing, based on the not based on the time of execution like a regular database. Athena does not have a fixed cost for 24/7 database running, even if you don't use it. No, Athena does not have any fixed cost. You only pay based on how much data you are scanning, and that's also a pretty interesting thing in my opinion. The official pricing is actually $5 per terabyte. So if your data set is much smaller than this, if you have 10 or 20 or 30 gigabytes, you can easily scan it every day, multiple times a day, and still pay way less than a few cents of a dollar. So I think this is pretty convenient. It is serverless because if you don't run any query, you don't pay anything. And you need to compare this to the traditional data warehousing world, where you would probably pay 200, 300, maybe $500 per month fixed, whether you use the data warehouse or not. So different model, right? There are a few best practices. Athena, for example, supports partitions. So if you want to optimize the execution time and also the cost of your queries, you can structure your data as follows. So you can have a partition name equal partition value in a folder, right? So you structure your S3 objects this way, and Athena will be able to automatically recognize the partitions in your schema. So you can make a where clause in your query saying like where year equal 2018, and Athena is going to be able to only query data in that folder on S3. And because you're scanning a very small subset of your whole data set, it's going to be faster and cheaper. I love this of Athena. There are, of course, other best practices, and one of the best practice is to use a columnar format like Apache Parquet, the one that I've mentioned with Data Firehose. Because if you use Parquet, it's like every single field in your schema is a partition. Okay, so if you are reading only 1 or 2 fields out of 20 in your schema, you are only reading a very, very small subset of your data. And so you're optimizing even more the cost and the performance of your queries. There are even more advanced use cases for this in this space where organizations and universities are building, state-of-the-art MapReduce kind of architectures based on S3 and Lambda, maybe a little bit of DynamoDB to keep track of the state. But you can really build a lot of impressive stuff when it comes to data processing at scale with using serverless architectures. There is actually a real world example implemented by the University of California in Berkeley called PyRen. This is also an open source project, and they reached crazy huge scale up to 40 teraflops of compute power. Okay, this would be even just 10 or 15 years ago, like in the top 50 or top 100 most powerful computers in the world. And now you can have it on AWS in a serverless fashion without any upfront commitment, without any contract, without any physical hardware investment. Maybe just for a couple of hours, you do your super crazy computation and then you tear it down, you should switch it off. So I think this is the power of the cloud, this is the power of serverless for even for analytical purposes, not just for websites and web applications and RESTful APIs. If you're interested in this world of scientific computation, the guys from Berkeley, they also built a NumPy version. If you know NumPy, it's a scientific, numerical matrix manipulation library for Python. And they've built like a NumPy version built on top of PyRen, so running on serverless. If you need to invert a matrix or multiply matrices together and do all sort of matrix multiplication stuff, linear algebra, you can have a look at this paper too. So guys, this is what I have for you today. We talked about serverless, what it is, where it might help you, whether you are a startup an enterprise, a consulting company, or even if you're just building your own side project and you just want to have fun. I hope it's clearer to you what is serverless, what you can do with it. I hope you are excited about building a website or about building a data ingestion and data processing pipeline with fully serverless services like Kinesis Data Firos, Amazon Athena, AWS Lambda, and so on. So let me know what you're going to build. And if you have a few questions, I'll be available for a while. Now, thank you for attending, and thank you everyone for joining us this afternoon. So I've not mentioned much about the cost of AWS Lambda itself. Actually, many developers ask me, okay, I like that you have the free tier and I can do up to 1 million invocations per month for free, and it's great. It's not even only the first year, it's forever. So forever, up to 1 million invocations per month is free, and I can build a lot of stuff with it. But I'm a startup, or I have a product that is going to be, I don't know, 10x or 100x in 6 months. So what happens when I get out of that 1 million invocations? Well, I don't know why they're worried, to be honest, but I understand you might think, what happens? Wow, maybe you go from 0 to $1,000 per month. No, after the first 1 million invocations, the next million, it's like $1 or $2. Okay, so you can really scale linearly. We provide 1 million per month, free forever, and the second million will be like $1 or $2, and the third million the same. So you can scale up linearly. And what happens usually is that if your load is scaling quickly, like 10x, it's likely that also your revenues or your visibility and the consumption of your customers is going to grow 10x. So as long as you have some margin on top of your architectural or infrastructural cost, this is not going to grow exponentially for you. So it doesn't go out of control. It's pretty linear, even sublinear. So what are their best practices to avoid DDoS attacks, which blows up the bill? Oh, that's a good question, actually. So that's a fun way of putting it. That people tend to say, yeah, there used to be DDoS attacks, but nowadays in practice you don't really have DDoS attacks anymore because you can scale up to almost infinity. So the problem is more like a wallet denial of wallet kind of attack. So if you're using services like CloudFront and API Gateway, so you already have, an SLA, you already have DDoS protection from the CDN side of things. So if CloudFront detects a DDoS, it's going to block it. It's not going to go through all the way to your backend. So you're going to pay for it. So that's the first layer of protection. But if if the attack that we're talking about is not enough to be blocked at the edge and it still reaches your backend, I would recommend using a rate limiting. So I think by default, when you publish an API gateway endpoint, there are no throttling or rate limiting logics applied to that endpoint. So in general, it's very unlikely that you don't need it. Okay, so always think about what's my average use case. Okay, how often are my typical or even my very regular customers or users going to call me? Is that, I don't know, 100 invocations per minute? Okay, is it supposed to be enough based on my application RESTful patterns? So I think a second layer of protection could be there to be able to automatically block and return a "I'm sorry, you have been rate limited" kind of response, and then you can handle that on the client in case you have been blocking legitimate users. Maybe tell them to retry in a minute. Another layer of protection, but that's more of a monitoring way of protecting yourself, is to set up a budget warning. So what you can do is that you can you can receive emails to your personal email or to an alias, so more people are watching this, not just one. Not based on the current spend, but based on the expected spend. Okay, so at any point in time in the billing dashboard of AWS, you can see the current spend and the expected one. So what you are expected to spend at the end of the month based on the current usage. So what I usually do and what I usually recommend is to set up a warning on the expected spend. So based on the historical bills that you had in the past, you can probably configure this warning to be able to catch if there is something that is really wrong and you're getting 1000x the request that you usually had in a day or in an hour or in a week. So with that kind of warning, it's not an automatic protection, but at least you have visibility into the problem and you can stop or take down the API and redeploy it to another URL or to another domain, or take measures, right? I think the problem of DDoS is that, especially nowadays that you can scale horizontally up to almost infinity, is that you don't really notice because customers are complaining, because maybe nobody's complaining. You're getting hundreds of thousands of requests and they are all succeeding, but you need other types of warnings that are not your customers complaining, but you need to monitor, maybe using CloudWatch or using other custom metrics, what's going on in the system. Let's take another question. Okay. So does the third-party authentication is going to affect any performance behavior as request is leaving AWS and going to Google, etc., and so on? So that's a valid point. So when I showed you the custom authorization logic that you can implement with the API gateway with the custom authorizer, one thing that I didn't mention is that custom authorization logic doesn't happen at every single request. It's actually cached, and you can configure how often, for how long it's going to be cached. So there is, of course, a little delay if you want to run, a signature verification algorithm, or if you need to talk to the identity provider, that might be a few hundred milliseconds. But keep in mind that it's not going to be for every single request. Okay, you can cache the result of the custom Lambda authorizer. Let's see, let's take another question. So for generic reporting purposes, do you suggest using a serverless architecture? Yes, I think what I've shown you with Kinesis, Firos, and Athena and QuickSight, I couldn't really show you QuickSight really, but it's super, plug and play, click and point and click kind of reporting dashboard solution. So I've actually seen it used for typical reporting solutions. Yes, it kind of depends on where the data is. If you are able to use Athena and Firehose, and if you are in control of the whole pipeline, from where the data is coming to where you store it, to how you query it, and to how you visualize the aggregations, you can build it fully serverlessly. Of course, if you are in control mostly of the second half, the data is already somewhere and you only need to analyze it and build reports. Maybe you cannot use Athena because the data is not on S3. Maybe the data is on a PostgreSQL database or on a data warehouse. You can still use QuickSight in that case. So at least the visualization and the data exploration side of things does not run on a server, or you don't have licenses issues and stuff like that. But yeah, I would definitely recommend the whole pipeline or even parts of it as a serverless data reporting. So another question, how does using CloudFront improve upload speed? Okay, that's a good question. So you can use CloudFront. I mean, in the majority of cases, you use CloudFront to distribute content to, using an edge network of 200 plus edge locations around the world. But you can use actually the same network for accelerating requests. Also, if they are not read requests, you might have a post or a put request, maybe for uploading a file. So it is accelerated, and the same mechanism holds for another feature called S3 transfer acceleration powered by CloudFront. It works because of these 200 plus edge locations around the world. So based on how far you are from an AWS region, you might actually be able to very, very quickly perceive it. So my suggestion to test it is, unless you are in the same city of an AWS region, so it's very close to you. If you are in a slightly more remote region and you are closer to an edge location than to a region, it's pretty easy to test. You take a bucket in the closest region to you, and you try to upload, I don't know, 50 or 20 megabytes to that region. And then you enable transfer acceleration and you try to upload that same object to S3 by using transfer acceleration. So instead of talking directly to the AWS region through the internet, you're going to talk to the closest edge location near you. And that might be several network steps closer to you. So you don't go through the public internet. You maybe do 1 or 2 steps using your local internet service provider, and then you reach the Amazon global network as soon as possible. And from there, it's all using, everything happens using the Amazon global network. So that's much faster than the regular internet. But it's kind of tricky to test these things because it very depends on how far you are from a region or from an edge location. But I've done a few tests. Maybe do a test by using a region in Europe or a region in the United States, and you will see a pretty considerable difference. Wow, we have a lot of questions. Thank you, everyone. Let's try. Let me have a look of all of them so I know if there are recurring topics. Okay, so how to send data to Kinesis from the front end. Is there any front end library available that we can use? Yes, you can just very simply use the AWS SDK. So you can talk directly to Kinesis from the browser or from the mobile application, but you will need to have credentials to do that, right? So either you use Cognito federated identities to get temporary credentials, and then you can talk directly to Kinesis, whether it's data streams or data files. The interface is basically identical. You can also talk to an API gateway, which is connected to Kinesis. So in this case, the API call might be unauthorized, might be even from anonymous users if you want to track also anonymous activity. A third option that might actually simplify a few things is if you use AWS Amplify. So there is a component called Amplify Analytics, and from the front end, it's much, much, much easier to integrate with that. So you have another abstraction layer in your code. So you would do something like amplify.analytics.track, and that takes care of the whole process of configuring Kinesis and doing all of that, all the requirement provisioning of cloud resources for you. Another question. Okay, I want to use PHP in my Lambda runtime. So PHP is not on the list of natively supported runtimes for Lambda, but there are custom runtimes, and there are even other community libraries that allows you to use PHP with Lambda. So I know of at least 2 or 3 custom runtimes and projects that allow you to do that. So it's, if you really just look on Google for AWS Lambda PHP library, you know, there are community contributions happening there, so it is possible. There are even a couple of frameworks developed by an AWS community member from France, if I don't remember wrongly, that, you know, he's been building a couple of interesting projects around PHP and Lambda. So have a look at that. It's definitely possible, and it's fast, and it's quite in line to the idea of serverless, where for every request you get the whole PHP stack up, return the response, and then die. It's kind of similar to the idea of AWS Lambda itself. So these are not 2 completely different worlds if you think about it. So what is the purpose of database proxy in AWS Lambda? So I've mentioned the RDS proxy as a new service that is now generally available. And there are mainly 3 benefits from using RDS proxy. The first one I've mentioned is the idea that RDS proxy will go and fetch username and password, you know, your credentials. So you don't really have to hard code any credential in your Lambda functions, or you don't have to fetch from an external service yourself in your Lambda function, because sometimes you don't really want the same person or the same team responsible for building the Lambda function or deploying the Lambda function to have access to the centralized parameter that contains the database password, for example. So RDS proxy will take care of that. Lambda talks to the proxy talks to the database by using the correct database username and password. The second advantage is that it will manage the connection pooling. So usually with a relational database, you have a limited number of connections. And because of that, with Lambda, you can scale horizontally much faster, you know, much broader than the number of connections that the database has available. And you usually want to cache the connection across invocation. So it's very easy to saturate the number of connections that you have. So the proxy will take care of that problem as well, and will allow you to use the right connection without saturating the connection pool. And a third advantage is that if your database is using multiple instances, if you are maybe in multiple availability zones, and if you are scaling horizontally with read replicas, for example, in case the primary node goes down, or in case the read replica that you are reading from goes down for any reason, the proxy is going to redirect the current connection to another available instance without interrupting the connection on the Lambda side, so in a very transparent way. So I think these are the 3 main benefits that comes from using the RDS proxy, at least for now. Maybe more features will come in the future. Okay, which AWS database service do you suggest for application that will have 10 million insert and update requests per day? So 10 million per day is not super crazy. It's still already a pretty interesting scale. It depends. If you're talking about 10 million inserts a day, it means that your write throughput is very high, and you will very quickly reach a scale that might easily kill a relational database. So I would actually recommend a NoSQL database. For this kind of workload, a database like Amazon DynamoDB might be ideal if you really have this high throughput of inserts and updates. The challenge might be the schema of your table. How do you update those records? Do you always have the primary key? Do you need a global secondary indexes? You know, what's your access pattern. Writing is easy. You have to look into your read access patterns to understand if DynamoDB might be a good fit. Usually it is, and usually you are okay with constraining the schema or with constraining your access pattern if you can achieve the right throughput that you need. So I would recommend Dynamo for sure. There are other options. You can use DocumentDB. That's a MongoDB compatible database. There is managed Cassandra. Amazon Keyspaces is basically a managed Cassandra. So all these NoSQL databases would definitely help you with this high throughput, high write throughput kind of workloads. But that also depends for how long you need to keep this data. If you have 10 million inserts a day, but then you only care about the data for a few days or for a week, and then you can forget about it. There might be other options. You might be able to use an in-memory engine like Redis or other options. Although if this is critical data for your business, maybe you want to use a more persistent storage as well. Okay, I'm reading a few questions. So what are the ways to ingest data to AWS S3? Well, there are a million ways to ingest data to S3. The one I showed you today was using Kinesis Data Pyros. I think that's the easiest, that's the most serverless option out there. There are many other. It's even hard to count them. There are countless libraries that can put or synchronize your data to S3. If it's not trillions of objects or petabytes of data, you might as well just do AWS sync, AWS S3 sync command from your laptop or from your virtual machine, and just sync the local content with the bucket. That's usually pretty quick. For this kind of use cases, always remember to enable the multi-threading functionality of the AWS SDK or the AWS CLI. If you use multiple threads, your bulk uploads to S3 will go way faster. Even if you do it from Lambda itself, you get multiple cores in Lambda after 1.5 or 1.8 gigabytes of memory power. So you might be able to go faster if you use multi-threading. Okay, thank you everyone for the great questions. Thank you for staying with us. And if you want to reach out, if you have other doubts, feel free to reach out to me on social media, or feel free to reach out to your local AWS friends. I'm based in Italy, but feel free to follow me and to direct message me if you have questions about serverless. Thank you, everyone. See you soon.